be able to ask it. So if you have a question, please put it in the Q&A. And with that, Hugh, it's all yours.
Well, thank you. I just hit the record button, so the questions that I just answered will not be in the recording. Sorry about that. I'll try to remember next week. Okay, I'm going to share screen now so you can see my visuals. So let me get that started. Okay, so I'll be seeing my first slide. And I want to thank all of you who've been communicating with me in social media and sending emails. Appreciate the suggestions. A lot of you have been wondering if we're going to do a skeptics forum with this Zoom feature. We're going to try to get that scheduled. A skeptics forum is where I don't do any teaching like you're going to hear me do now. We literally take the entire time for questions from skeptics, Christian skeptics, as well as non-Christian skeptics. We have just one rule for that: don't bring any softball questions. We want serious questions brought to that. So we'll let you know a date when we have that scheduled. So, and a number of you were asking me whether the material I was presenting last week was original. And the answer is yes. You will not find it in the scientific literature. So it's based on my private analysis of the data that we have on extrasolar planets. So it's going to be part of the book I'm working on. It has a tentative title, Interior Designs. And it's a book where I'm actually talking about the interior design of our super galaxy cluster, our galaxy cluster, galaxy group, our galaxy, our star, our planetary system, our moon, our Earth, the interior layers of the Earth. That will be the book. There's going to be nothing in the book about how to furnish your home. But I think our staff here wants the title Interior Designs. We'll see who we pick up with that. And what I did last week was something I've done when I was working on my book, Weathering Climate Change, was actually use this paradoxes class as an initial sounding board. And I just garnered your feedback. As I'm doing the research and the initial writing, it always helps to get some good feedback as to how we can improve it, what needs to be dropped, and what should be added. And I already got some great suggestions from you. And I'm going to continue with the chapter I'm working on, which is basically the interior design of the system of planets, or solar system, and in contrast what we see other planetary systems. I covered basically what's in the book concerning the smaller planets and the exoplanet catalog. Today I'm going to focus on the best, the most thoroughly studied and the most accurate data we have in exoplanets is for the gas giants. And I'm going to be, in fact, I've written a lot this week in the book just on what we've discovered about gas giants and how it reveals the marvelous design of the system of gas giants in our solar system. New designs literally being revealed just within the past few weeks. So this is probably going to take 2 weeks. So this will be part 1 today, and I'll get part 2 next week. And probably the 3rd week, we'll get into the interior design of our star. Our star is unlike any other star that we know. We've studied literally tens of millions of stars, and our sun is the only one that has these unique interior design features that permits it to host a planet on which advanced life exists. And likewise, with this chapter I'm writing on now about our planetary system, it's revealing that our planetary system is unlike any other planetary system. I mean, we now have discovered well over 3,000 exoplanetary systems. And so I'm going to share with you just some details of what we've been discovering about the gas giant planets that reveals how special our solar system is, how marvelously designed it is to make possible a home in which advanced life can exist. Bottom line, literally every planet in our solar system, every one of the 8 planets, has these very exquisite fine-tuned designs that makes possible advanced life here on planet Earth. We literally need every one of them to be exactly the way they are. And I'll be sharing with you too this morning and this afternoon about how each of the planets stands alone. I mean, my colleagues have been busy searching for a twin of the Earth, a twin of Jupiter, a twin of Saturn. Anyway, I'm getting ahead of myself. Let's jump into this and to see where we go with this. So I need two computers to make this work. So let me get my second computer working. There we go. So I do have quite a bit on our planetary system in weathering climate change. What I put in that book is how the masses and the specific orbits of all 8 planets need to be exactly the way they are in order to set up this period of extreme climate stability in an ice age cycle that we're enjoying here on planet Earth and is uniquely making possible a global human civilization. So yeah, you can look at that chapter in weathering climate change. And yes, you can get a free chapter of the book by going to reasons.org/Ross. And as I mentioned, okay, here's a couple of Bible verses that I think will help where, let me get my other computer caught up here. Yeah, a little bit out of sync. Anyway, in Psalm 24, verse 1, and Paul repeated the verse in 1 Corinthians 10:26. Anytime you get the New Testament repeating a verse from the Old Testament, is letting you know that it's communicating something very important. The earth is the Lord's and everything in it, the world and all who live in it. Basically making the point that God specially designed the earth so it can support the life. He is the author and the manufacturer of planet Earth, and likewise, he takes credit for being the manufacturer of all life on the planet Earth. But I think we can say the same thing about every planet in our solar system. None of them are accidental, none of them are random. Each one of them has been designed to make possible a planet Earth that is filled with millions of species of life and ideally fit so that human civilization can flourish. Jupiter is the Lord's and everything about it and all who depend upon it. And likewise, I think we can say the same thing about Saturn and literally every one of the 8 planets in our solar system. But I'm going to be focusing on the gas giants. And I didn't show you this last week, but I think somebody asked me if I could do this. So this is what I put together for you. This actually shows you the relative sizes of all 8 of the solar system planets. So it just gives you an idea how much larger Jupiter is than the Earth. You can literally fit more than 1,000 planet Earths inside Jupiter. Likewise, you can fit 1,000 planet Earths inside the planet of Saturn. And then you see the Neptune-sized planets, Uranus and Neptune, how much bigger they are. And this also shows you just how tiny Mercury and Mars are relative to Venus and the Earth. And again, from last week, this is how astrobiologists, planetary astronomers classify the extrasolar planets that they're discovering. 4 categories. A planet is either a gas giant, a Neptune type, a super Earth, or a rocky planet. Our planet Earth is classified as a rocky planet. And gas giants are defined as planets that are more massive than Saturn. Jupiter is 318 times the mass of planet Earth. Saturn is 95 times the mass of Earth. Any planet more than 95 times the mass of planet Earth is classified as a gas giant planet. And this is an update from last week. There's actually been some gas giant planets that have been discovered. Some have been reclassified. So there's a slight adjustment from what I showed you last week. Classifying gas giant planets according to the distance from their host star. So a warm gas giant planet is a planet that is anywhere from 0 to 1 astronomical unit. A little bit technology here. 1 astronomical unit is the orbital distance of the Earth, about 93 million miles. So any planet that's closer than 93 million miles to its star is classified as a warm giant. The cool giants are gas giant planets that are between the orbit of the Earth and the orbit of Jupiter. Jupiter orbits at 5.2 times the distance from the sun that the Earth does. The cold giants are those gas giant planets that orbit between Jupiter and Neptune. Neptune orbits out at a little more than 30 times the distance that Earth orbits the sun. And distant giants are gas giant planets that have been discovered that orbit more than Neptune's orbital distance about the sun. And what's changed since last week is the population of cool giants has gone up. Also, another distant giant has been classified in that category. And basically, the cold giants are slightly rarer than what I told you last week. So, comparing these gas giants, what we see in our own solar system, it's about 4% of exoplanetary gas giants are in the cold category, whereas in our solar system, they make up 100%. And if they didn't make up 100%, there'd be no life possible. A problem with a cool gas giant or warm gas giant planet, their mass is so great that if they're any closer to their host star than Jupiter is, it would disrupt the orbits of small rocky planets like Venus and Earth and cause them to be uninhabitable. So it's a good thing that all of our giants are cold. It's also a good thing that they're not distant. I'll share later why we need the gas giant planets. We didn't have gas giant planets, there'd be no life possible in our planetary system. And this is new, something I've developed just based on my research of this past week, comparing cold giants and exoplanetary systems with cold giants in our solar system. And what you see here is that in exoplanetary systems, they make up 4% of the gas giants, whereas in a solar system, they make up 100%. But the mass of these exoplanetary gas giants is much larger. The average mass of these gas giants is 16.44 times the mass of Jupiter, whereas in our solar system, the average is very low, just 0.65, the average of Jupiter and Saturn. 82% of the gas giants have an eccentricity greater than 0.1, whereas none of them in the solar system have an eccentricity greater than 0.1. I'll tell you in a minute what an eccentricity is all about and why it's so critical for life in our planetary system. And 82% have an eccentricity greater than 0.1. If we were to average the eccentricity of all the gas giants discovered outside of our solar system, including the 18% that are less than 0.1, the average eccentricity is 0.32. Whereas for a solar system, the average is 0.05. The other thing we notice is in exoplanetary systems, the cold giants orbit much more distantly than the cold giants in our solar system. It is true that the closer a gas giant is to its host star, the easier it is for astronomers to discover them. And therefore you would think that they would tend to be on the close side, but notice the big difference. There's a difference of 6 astronomical units between the distance of the solar system gas giants and those of exo gas giants. So even though it's more difficult to detect the more distant ones, we're finding many more distant ones than we are in our solar system. So almost twice as distant as what we see in our solar system. And so for those of you who are not familiar with what eccentricity is all about, here's a quick review from what you learned when you were taking high school geometry. And so this shows you an ellipse. All planets orbit their stars with an elliptical orbit. Isaac Newton's physics explained why they must be elliptical orbits. In the case of our solar system, the elliptical orbits are very close to circular, but this is more typical. And the definition of the eccentricity is the distance from the center of the ellipse to the foci of the ellipse. The ellipse has two foci, and so that C there represents the distance between one of the foci of the ellipse and the center of the ellipse. And the B is what we call the semi-minor axis, which is the shortest, half the shortest diameter of the ellipse, whereas the semi-major axis is half the longest diameter of the ellipse. And the eccentricity is C divided by A. And so the greater the eccentricity, the flatter the shape of the ellipse. If the eccentricity equals 1, it's so flat it's a line. The eccentricity is 0, it's a perfect circle. And so this next slide shows you the eccentricity of the Earth about the Sun. This is actually fairly accurate, showing the difference. The eccentricity does vary a little bit. The reason why it varies is because of the gravitational influence of Jupiter and Saturn. And I wrote about this in my book, Weathering Climate Change, making the point, if it was not for the gravitational influence of Saturn and Jupiter, the shape of Earth's orbit wouldn't vary much at all. And therefore, it wouldn't be a significant driving factor for the Ice Age cycle. We literally need Jupiter and Saturn to be the mass that they are and orbiting the sun where they are in order to generate a perfect Ice Age cycle that makes possible the existence of billions of human beings on planet Earth. You can read Weathering Climate Change. That will explain to you why we have to have an Ice Age cycle for billions of people to possibly exist on planet Earth. And this fits right in what the Bible talks about, how it's God's goal in creating human beings and placing them on planet Earth, that they'd be able to be fruitful and multiply, as it says in Genesis 1, and it says in the last book of the Bible, be fruitful and multiply to a point where their population would be uncountable, which means it would be in the billions. We're there right now, but for billions of people to live on planet Earth at one time, it's necessary that we have a just right Ice Age cycle, and we wouldn't have that if it wasn't for the gravitational disturbance of Jupiter and Saturn on our planet. But this is the effect it has. It makes for a very subtle variation in the eccentricity of the orbit of the Earth about the Sun. Now, what I'm going to show you in the next slide is what is typical for exoplanetary systems is that the eccentricity of the elliptical orbit about the host star is much bigger than it is. It's actually bigger than what I'm showing you here. For most of them, it's quite a bit flatter than what you see in this particular one. This shows you an eccentricity of about 0.1. As I told you before, the average is 0.32. And so it's actually much more eccentric than this on average. But almost all of the discovered exoplanetary gas giants have eccentricities that are greater than what you see here in this graph. Now, an eccentricity that large, and particularly with so many of the gas giants being closer to their host stars than is to Jupiter, this generates orbital chaos for the small planets that are orbiting more closely to the host star. Planets like Mars, Mercury, Venus, Earth. In fact, it would even generate chaos for the super Earths, as I mentioned last week. So now, if we were to compare pardon me, let me pull this back one. Okay. I'm missing a slide. It's present on my second computer, but not on this one. Namely that the average exoplanet eccentricity, this is for all the planets. For all the planets, it averages 0.26. And with 0.26, the ellipse would be a whole lot flatter than what you see on this particular slide. And we compare that with our solar system. Again, we're averaging for all the planets, not just the gas giants, but for all the planets in our solar system, the average is only 0.06. So in comparing 0.26 with 0.06, and I think what's particularly significant, if we were to only look at the 6 largest planets, because the planets that have the largest eccentricity in our solar system are Mercury and Mars, and for very good reasons. They have very small masses, and because they have such small masses, they're much more heavily disturbed by the gravity of Jupiter and Saturn and Uranus and Neptune than is the case for Venus and the Earth. And so if we were to take those 2 out, the average eccentricity for the remaining 6 planets is 0.03. So it literally drops by a factor of 2. Mercury has an eccentricity of a 0.2, but that's because it's such a tiny planet. So matter of fact, astronomers have calculated that within the next 5 billion years, there's a high probability that Mercury will be kicked out of the solar system by the ongoing gravitational influence, particularly of Jupiter and Saturn. So 0.03 compared to 0.26. Now, what I put in my book, Improbable Planet, I was talking about the decades-long search that planetary astronomers have been undergoing to try to find a planet in the population of exoplanetary systems that's sufficiently like one of the planets in our solar system. So just like they've been looking for a twin of the sun, they've been looking for a twin, not just of planet Earth, but of any of the 8 planets in our solar system. And back in 2010, a paper was published, and a subsequent paper came out in 2011, basically saying that they have found a remarkable Jupiter twin. And so I'm going to just share with you. Okay, Jupiter, we're going to compare the mass of Jupiter to the mass of this discovered planet. Jupiter orbits the sun at 5.2 times Earth's orbital distance, 5.2 astronomical units. It's got quite a small eccentricity, just 0.048. But what happened in 2010 and 2011 was the announced discovery of a planet orbiting the star Upsilon Andromeda. It's actually a star you can see with a naked eye. It's about 4th magnitude. And earlier they had found 3 planets orbiting. This was the discovery of a 4th planet. So it would be Upsilon Andromeda E, and how it had a mass that was 6% larger only than the mass of Jupiter. Although notice the plus sign there. That's the mass of this planet, assuming that the orbital plane of Upsilon Andromeda is aligned with the telescope's, the astronomer's telescope. If it's not, then the mass goes up a little bit. But 6% more massive, and it's orbiting its star at virtually the same distance that Jupiter orbits the sun, 5.25 instead of 5.2, and it's got a nearly circular orbit, actually even more circular than Jupiter. So this was the announce. We finally found a twin of a Jupiter, a relatively close twin of Jupiter. But what I wrote in Improbable Planet is that yes, Upsilon Andromeda E just does match remarkably close the mass of Jupiter, the orbital distance, and its eccentricity. However, in 2 important ways, very important ways, it's radically different from Jupiter. So if you look at just these 3 characteristics, you could claim that they have found a good analog of Jupiter. But if you look at 2 more easily measured features, you see that it radically departs. Namely that one of the major features of Jupiter, it's the most massive planet in the solar system. And of all the gas planets, gas giants as well as Neptune-type planets, it orbits our solar system more closely than any others. This is not the case for Epsilon Andromeda E. And so, as this next slide shows, for example, there are two very much larger gas giant planets in the Epsilon Andromeda system that orbit that star significantly closer than Epsilon Andromeda E. And so we have one that comes in at a whopping 14.57 times the mass. Incidentally, that is actually a true mass. In fact, the very latest measurement, I need to update this slide, puts the mass at 13.98. Because they've been able to measure the three-dimensional geometry of the planets of the Epsilon Andromeda system, we now have exact planet masses within the error bars, but the new mass is 13.98. But that's the 14 times more massive than Jupiter. And look where it orbits. It actually orbits Epsilon Andromeda even closer than the Earth orbits the sun. And with a big planet that close to its sun, it's going to generate utter chaos for any smaller planets. In fact, a planet that massive orbiting that close guarantees that there won't be any small planets in the Epsilon Andromeda system. And moreover, it's joined by another huge gas giant, this one coming in at 10.19, and that is an accurate mass. In fact, the latest result puts it, I think, at 10.49 times the mass. Yes, it's 10.49 times the mass of Jupiter, and that orbital distance likewise has been accurately measured, about 2.5 times the orbital distance of Earth relative to the sun. But the combination of these two huge gas giants orbiting, and look at the eccentricity. That's a mistake there. The eccentricity is not 2.74, it's 0.274, and then 0.24. But these planets, with their enormous eccentricity, their huge mass and close orbital distance, again guarantees there will be no closely orbiting small planets, either rocky planets or super Earths or even Neptunes, anywhere closer than Mars is orbiting the sun. And moreover, they've just discovered another planet that it orbits very close to Epsilon Andromeda, close enough that it has a stable orbit in spite of the existence of Epsilon Andromeda C and D. Epsilon Andromeda B orbits the star with a revolutionary period of only a few days. So it orbits close enough that it can withstand the gravitational tugs and pulls of C and D. Its mass is 1.7 times the mass of Jupiter. So Jupiter has 68% of the total mass of all the planets in our solar system. Epsilon Andromeda E actually is less than 4%. And so that's a major difference. And Epsilon Andromeda E is the most distant of the big planets orbiting orbiting the sun, or orbiting Epsilon Andromeda, whereas in the case of our solar system, Jupiter orbits more closely than all the others. And these are critical characteristics, very easy to measure in exoplanetary systems that we don't see in any other gas giant planet amongst the thousands that have been discovered since 1995. Now, Epsilon Andromeda E is the only only exoplanet that comes anywhere close to the characteristics of a solar system planet. However, a paper was published that basically shows that Epsilon Andromeda E needs to be dropped from the list of because a new analysis of the Lick Observatory measurements of the past history of Upsilon Andromeda basically shows that there was a change of an instrument made. And if you take into account that change of instrument that was used to do the radial velocity measurements to determine the orbit of the planets in the Upsilon Andromeda system, that basically gives us a 99.9% probability that Upsilon Andromeda E does not exist. And so if you look at the latest exoplanet catalogs, you will not see Epsilon Andromeda E. It's been dropped. And so all this excitement about finally finding a twin about one of the solar system planets actually now no longer is the case. It's been dropped. It wasn't a twin in the first place because it was missing two important features of Jupiter that makes life possible in our solar system. But now we recognize that the planet, to a very high probability, does not exist, 99.9% probability that it does not exist. This is one of the newer releases of the image of Jupiter taken by the Juno spacecraft, and shows you the giant red spot. When it was large, the red spot's now quite a bit smaller, but also shows you it's not the only red spot. You can see a tiny red spot just to the left center. And you get these red spots when you have very high velocity, long-lasting hurricanes on Jupiter. The big red spot is a giant hurricane. That little one you see there is a small, but still very high velocity hurricane. And what I'm going to show you now that we no longer have Upsilon Andromeda E, what are the best twins that we can find for Jupiter in the exoplanet catalog of nearly 4,300 discovered planets outside the solar system. What we see here is that here's Jupiter. So we're going to compare everything to the mass of Jupiter, and the orbital distance is 5.2 astronomical units. Its eccentricity. There's only one of the 5 twins that have been found, and I'm calling them analogs because they're really nowhere close to the characteristic features of Jupiter. But it's the best that we can find amongst all the gas giants in the exoplanet catalog. And where we've discovered another planet in the system, I make note of that. Of these 5 analogs, only one of them do we have the discovery of another planet. And actually, it's the one that's the best. So these are actually in order. So BLG 0026LC. Actually, the name of this planet is much longer. I just clicked it and gave you the last part of it because it's enough to identify it. But this is the best Jupiter analog that's been discovered. Notice its mass is considerably less than the mass of Jupiter. And it orbits interior to its star than Jupiter does. So Jupiter's distance is 5.2 astronomical units. This one is 4.63. There's no measure of its eccentricity, the shape of its orbit, but there is an inner Neptune in the system. And the presence of that inner Neptune, along with its gas giant, guarantees that there's no possibility of another planet in the system on which life can exist because these 2 planets are guaranteed to generate sufficient orbital chaos to rule that out. The next best one we can find, you can see it's quite close to the characteristics of BLG 0026LC, is BLG 1269LB, slightly more massive than BLG 0026LC, and has virtually the same kind of orbit, but no measure of its eccentricity and no discovery whether it's got another planet in the system. I'll talk probably next week about why these gas giants typically eliminate the possibility of small planets in their system. And then we have one that's more massive, 28% more massive than Jupiter, and actually closer. So the fact that it's more massive and closer, again, means greater chaos in that system for rocky planets. And then we find 2 that are 2.5 times, 2.6 times the mass of Jupiter, But in one case, we see in BLG 235LB, it's got virtually the same orbital distance that Jupiter has, but it's 2.6 times the mass of Jupiter. That's mass is too great to permit a rocky planet in the same system on which life is possible. And the next best twin, same mass, but a greater distance. 11 times, it's actually more distance than Saturn orbits the solar system. But look at the eccentricity, 0.49, which means it's got a very flat ellipse. And with that flat of ellipse, that means it's going to come in very close to its host star at certain points in its orbit and very distant at other parts. And so when we talk about that 11.1, actually with an eccentricity of 0.49, it's going to come in closer to its host star than Jupiter is presently, and then go even farther out. And so as you can see here, these best Jupiter analogs are nowhere near close to the characteristic features of Jupiter. And so this basically, again, is giving us evidence that Jupiter has special design features that make possible advanced life in our planetary system. Well, I've used up actually more than my 30 minutes, so I'll pick this up next week. I'll show you the best analogs we got for Saturn, the best analogs we got for Earth and other solar system planets, and then exactly why we need Jupiter and Saturn to be exactly the way they are in order to get the comets and asteroids we need for advanced life to be on planet Earth. You might be worried about when the next asteroid or comet collision hits. I'm going to show you a number of crucial benefits we get from comets and asteroids, but clearly you don't want too many collision events from asteroids and comets. It wasn't good for the dinosaurs. It wouldn't be good for us if that were to happen anytime soon. We'll talk about that next week. And again, it's going to be original material. It's not the material you're going to find published in the scientific literature. I like to have original material in every book that I publish, but I also appreciate the opportunity to share with you, members of the Paradoxes class, because I think, being part of the class, I want you to be the first to hear about this kind of research we're doing at Reasons to Believe, but also I know a lot of you are in a position to give some good feedback, and I really do benefit from that. So with that, let me stop the share feature, and we'll get back to dealing. Okay, we'll take the rest of the time for questions. Mark will moderate, and this is a time where you can ask any question that you want. It doesn't have to be on necessarily the subject we're talking about. Of course, it can be.
Great, thank you, Hugh. Question from Stephen Poster from Spring, Texas. A UCLA-led team of astronomers recently suggested that the Milky Way's 4 million solar mass supermassive black hole, Sagittarius A with an asterisk after it, has a smaller 100,000 solar mass supermassive black hole companion in orbit around it. Two-part question. If this is confirmed, what will the naming convention be for the secondary supermassive black hole be? And what impact would a secondary supermassive black hole have on the fine-tuning of the Milky Way galaxy?
Okay, good questions. And yes, I'm aware of the announcement, and it needs to be confirmed. We have detected stars that are orbiting about that supermassive black hole. It's because of those stars we've been able to measure the mass of that supermassive black hole as accurately as we have. For there to be a black hole 100,000 times the mass of that supermassive black hole, it would have to be orbiting relatively close. And to have avoided detection up until this time, the very fact that we can detect stars orbiting close to the supermassive black hole means that if this discovery stands up, it needs to be orbiting quite close. And if it's orbiting quite close, we need to also come up with an explanation why it's not generating more disturbance. What we're seeing with that supermassive black hole is it appears to be surrounded by the equivalent of an Oort cloud of small bodies, bodies smaller than planets, because almost on a daily basis, we get these tiny bursts of energy coming out from the center of our galaxy, which is what you'd expect if you got a supermassive black hole about 4 billion times or 4 million times the mass of our star, the sun, consuming them. Is going to generate these small bursts as that little bit pieces of matter get sucked in to the supermassive black hole. But if you got another black hole, at 100,000 times the mass, then you would really predict a slightly different feature of these small little, almost daily energy bursts, tiny energy bursts going on. The good news is that even if we're talking about a naked supermassive black hole, where it's 4 million solar masses all by itself, what we're seeing over the past few decades of activity in the center of our galaxy tells us that our supermassive black hole currently is in a very quiet phase, much quieter than likely would have been in the past. But being in such an exceptional quiet phase, this is good news for us here in Planet. In fact, I've written a chapter about black holes in our vicinity in my book, Interior Designs, and perhaps I'll develop a talk on that for the class, because I'd like to get some feedback on that too. But what's really interesting is that the supermassive black hole in our Milky Way galaxy currently is an exceptionally quiet phase. The one in the Andromeda galaxy, where we're dealing with a supermassive black hole 100 times bigger than the one in our galaxy, likewise, it too currently is in a very quiet phase. And likewise, we got the really big supermassive black hole, more than 6 billion times the mass of our star, the sun, in the M87 galaxy, in the Virgo cluster, in the center of the Virgo cluster. Right now, the energy jet that's coming out of that is pointed away from our galaxy. And so everywhere we look about these supermassive black holes, currently our planet Earth and human civilization is in a quiet phase where we're not in danger from these things. If this 100,000 mass supermassive black hole holds up, again, we need to explain why it currently is in such a quiet phase as not to cause disturbing conditions. Of course, what would really be bad news for life on planet Earth if that 4 million solar mass black hole were to suck in that 100,000 mass black hole. That would be the end of all plant and animal life on planet Earth if that were to happen. But again, let's wait for confirmation. It definitely needs to be confirmed. But so yeah, I think I might give a talk on that at some point.
Thanks, Hugh. We have a question from David from South Orange County. I'm presuming that's South Orange County, California, USA.
Well, there's 3 orange counties in California, so.
Oh, well, whichever one he's in, we got a good question from him.
Only one in California, sorry.
In the young Earth creationist astronomy literature, I've read about claims of how the universe can be young. I have not seen them reference experiments that support their position. Do they have any support from science, or are their claims just speculations of what seems plausible to their audience, which appears to be mostly lay people?
Yes, I would agree, and it's a sad commentary that these young Earth creationists are really not engaging the secular scientific community about their scientific claims. And the Supreme Court back in the late 1980s actually put the young Earth creationist model on trial. A number of scientists came forward, but basically testified that the scientific evidence was just as strong against the young Earth interpretation as it was against the flat Earth interpretation. And when the judge heard that, then he said, well, on that basis, we can't try the worthiness of young Earth creationism to be taught in public schools on its scientific merit, we can't find any scientific merit. And therefore, they brought a number of witnesses who were theologians and pastors and basically testified that this was an interpretation of the Bible that was held by a minority within the Christian community. And therefore, the Supreme Court justices ruled, well, we rule in favor of this appeal from the young earth creationists. We would be favoring certain segments of the Christian community against others. And we're forbidden through the Freedom of Religion Act from the government taking action to favor one Christian denomination or one Christian segment against others. But they made it very clear in that Supreme Court ruling that any model of creation that has got some demonstrable scientific merit is permitted to be taught in the public education arena. And the presumption was that they'd be able to find some scientific merit, but the Supreme Court ruled that they couldn't find any. And that was back in the late 1980s. Today, there's even stronger scientific evidence against the young earth creationist model. And what I did in my book, A Matter of Days, I actually took on what young earth creationists consider to be their best scientific evidences for young earth and showed why each of their best evidences, indeed, once it's understood, is actually transformed into an evidence for old earth. And so, yes, but sadly, they are taking advantage of the fact that many people in their lay audiences don't have the scientific background to see where the flaws and the misinterpretations are taking place. On the other hand, I would share with those Christians, we've got multiple commands in the Bible. Test before you believe. 1 Thessalonians 5:21, everything must be tested. Hold fast to that which proves to be true. You say, well, I'm not a scientist. How can I put these tests to the claim? Well, you can take the claim and share it with your friends who've got advanced degrees in engineering and science and say, what do you think of this evidence? And if they all panic, then I think that's something you should not trust. Matter of fact, they came up in two major debates I had with leaders in the young earth creationist community, where the moderator asked just this one question to the young earth creationists. Can you give me the name of any scientist who, independent of a Bible interpretation, has ever drawn the conclusion that the earth or the universe is younger than many millions of years? And in both cases, the young earth creationist leader said, I can't think of a single one. I document that in my book, A Matter of Days. Those two leaders were Duane Gish, he has since passed away, and John Morris, who's the current president of the Institute for Creation Research.
Thank you. Craig McMahon has a question for you. Given the techniques we have available for detecting exoplanets, wouldn't one expect the average mass of cold giants and exosystems to be higher than what we find in our solar system? That is, if we have better instruments, wouldn't we tend to find more lower mass cold giants in exosystems?
Yes, and this has been a discussion in the scientific literature. Do we have a complete enough database to be able to do the kinds of statistical analyses like I've been doing here last week and this week? I'm not the first to do these kinds of statistical analyses. There's been several in the published scientific literature, but the last one that was done was 2 years ago. And interestingly, it too just focused on the gas giants, but made the point that the catalogs we have today are complete enough to be able to draw these kinds of conclusions. In fact, as I was pointing out today, what's interesting, when you look at the population of gas giants in these exoplanetary catalogs, you'd notice that they skew to much greater distances from their host star than we see in our own solar system. And yes, they're more difficult to detect, but notice that you anticipate that they would be closer based on the degree of difficulty, but in fact, they are more distant. I mean, what was a shock to the astronomical community is just how many gas giants they found that are orbiting close to their solar system. And I'll be explaining next week why that is the case. I mean, it stunned the astronomical community. but it basically caused them to say, there's so many of these warm and cool gas giant planets, there must be a reason why we're finding so many. Because one of the things, in fact, I'll be sharing with you this next week, gas giant planets can't form that close to their host stars. They have to form far away where Jupiter, Saturn, Uranus, and Neptune are, where it's cold enough for them to form, and they migrate inwards. So that'll be the subject of next week. And basically, we have the technology today where it's relatively easy to determine whether or not an exoplanetary system has got gas giants. The technology can discover them if they're nearby to their host stars and also they're far away. And keep in mind today, we've got over half a dozen different techniques for discovering gas giant planets. And some of those techniques actually favor the discovery of more distant gas giants than they do the nearby ones. So the direct image technique, for example, does. But it is true, the radial velocity technique does favor the discovery of the more massive gas giants and those that are closer to their host stars. But these other techniques actually favor the more distant ones. So, but the bottom line is, yes, we could use a more complete catalog, but the catalog we already have is more than adequate to favor drawing these kinds of conclusions that you see me drawing.
Thank you, Hugh. Tim Williams has a question for you. Weathering climate change predicts a coming ice age if warming occurs. The popular media tends to depict runaway warming as the likely result. Is the heat then cool story widely embraced in the scientific community?
Good question. It's widely embraced by those who actually have looked at the long-term history of the ice age cycle and have actually examined what happens to the North Polar Cap. It's not widely embraced by your rank and file climatologists. I mean, that's one reason why I put a couple of chapters in Weathering Climate Change, because I'm hoping to alert the community of climatologists, hey, this projection of runaway warming is not going to happen. If we warm the planet up, it's going to bring about significant cooling. And, you know, we've had runaway warming in the past. In fact, if you look at the long-term ice age cycle, when you come out of an ice age, you basically get runaway warming. But it doesn't lead to the evaporation of all the ice and water on planet Earth. It runaways to a point where the temperature hits about 2 to 3 degrees centigrade above where we are right now, and then things reverse and you get a runaway cooling. But the runaway cooling also is braked at a certain point, it stops, and then you get a significant period of cooling where the global mean temperature is about 12 degrees centigrade colder than what it is now, and then you come out of it. And what generates this cycle of going into an ice age and out of an ice age are the Milankovitch cycles. There's 2 chapters on that in Weathering Climate Change. But what really happens here, the problem of ongoing global warming, the global mean temperature has risen by 1 degree centigrade since 1950. If that were to continue at that pace, within about 200 years, the global mean temperature will be sufficient as to melt the summer polar ice cap. And if you melt the polar ice cap, in fact, in the year 2012, half of the normal polar ice cap in the summertime melted away. And even today, in fact, ever since the year 2010, the summer polar ice cap has been sufficiently melted away that you can take huge freighters and oil tankers over the Northwest Passage. You get open ocean water that for the first time actually allows that to happen. Back in my grade school days, our teachers were saying, we're never going to get a big ship through the Northwest Passage. There's just too much ice. Well, the planet's warmed up enough now where that actually can happen. And that kind of shipping is actually taking place. But if we were to melt all the summer polar ice cap, that would expose the Arctic Ocean to the heat of the sun. As it is, that polar ice cap reflects away about 60% of the heat and light of the sun that is incident upon it. But if that ice were to be melted and you got open ocean liquid water, that open ocean liquid water would now reflect sunlight with only 6% efficiency, which means the Arctic Ocean would be absorbing a huge amount of solar heat that it's not absorbing now. And what happens to that heat? It produces water vapor. And so water vapor would be wafted up off of the Arctic Ocean, and that water vapor will fall as snow over Siberia and Canada, over Greenland, and to a sufficient degree that within a short period of time, all of Canada and Siberia become covered with thousands of feet of ice, and even a good chunk of the lower United States would be covered by thousands of feet of ice. During the last ice age, for example, that ice sheet went all the way down into Southern California. Yosemite Valley was carved out by the retreat of ice from the last ice age. Excuse me. So, and the only reason why we don't have Canada covered with thousands of feet of ice today is it doesn't get enough rainfall. There's not enough water vapor coming off the Arctic Ocean to produce the quantity of snow that would be necessary for ice to accumulate. The average precipitation over the Canadian Shield, for example, is a little bit less than 10 inches equivalent per year. And with that little snow falling, it's not enough to accumulate over the summer. But if you jump it up to 20 inches equivalent, now the snow will accumulate with a short order. You got all of Canada covered with ice, all of Ohio covered with ice, Minnesota covered with ice, Oregon and Washington covered with ice, half of California covered with ice, and all that ice reflects away sunlight, and it actually dramatically cools the entire planet. If you put that much ice over Siberia, Northern Europe, and North America, then you're going to cool down the whole planet. And yeah, if we melt the polar ice cap, we're looking at 55% of North America being covered with thousands of feet of ice. Anyway, if you want the details, go to Weathering Climate Change. And again, you can get a free chapter at reasons.org/Ross.
Thank you, Hugh. We have a question. We don't have any open questions, but we do have
I lost your sound, Mark. Is everybody hearing Mark?
Can you hear me now?
I can hear you now. Yeah.
Okay. So I've got too many buttons going here. So before the session opened, when you started the recording, Doug McComb had asked a question about the Kent Hovind, and he wanted to make sure he got the response to that recorded. Would you mind answering it again if I posed the question again? There are no other open questions.
Yeah, go ahead. Pose the question again.
Okay. In a debate quite a while ago with Dr. Dino, Kent Hovind, the topic of Pangaea came up where Hovind mocked the idea of Africa and South America originating from one continent, even though the Bible refers to the world being divided in Genesis 10:25 in the days of Peleg. He said that Africa would have to be 35 to 40% smaller for Africa and South America to have branched off from one another. Is there a scientific basis to believe that there was once only a supercontinent? And if so, why would there being only one landmass originally appearing? Wouldn't it be more likely that islands would appear first here and there? After all, there were many tectonic plates moving underneath the Earth in the Earth's early days, were there not?
Okay, let me first address the dividing of the world in the days of Peleg. That's Genesis 10:25. And I believe that's a reference to the forming of the Bering Strait. If we were to go back 14,000 years ago, there was a land bridge joining Siberia to Alaska. It was as much as 500 miles wide. And starting 14,000 years ago, it became warm enough on the Bering Land Bridge that you could get various grains growing there, which means there would be food that could be harvested as humans migrated from Asia over that land bridge into North America. And that 14,000 year data is consistent with the earliest evidence we have for human habitation in North America, which is about little more than 13,000 years ago. From 14,000 years ago to 11,000 years ago, there was relatively warm passage possible over the Bering Land Bridge. But starting about 11,500 years ago, that bridge began to dramatically narrow as the sea levels rose. During the last ice age, the sea level was 390 feet lower, but starting about 11,000 years ago, the rapid melting of ice left over from the last ice age caused a dramatic rise in sea level, and that eventually formed the Bering Strait. Today, there's an 80-mile separation between the easternmost tip of Russia and the westernmost tip of the mainland of Alaska. And it's a treacherous strait. And until 100 years ago, it was not possible for humans to cross from Asia into North America, or for North Americans to get to Asia, because of treacherous it was to have a small craft navigating the Bering Strait. Very powerful currents go up through it. So you need modern day boats to make that possible. And so I believe that's what Genesis 10:25 is referring to, the dividing of the world in the days of Peleg. When the sea levels were much lower, the continents were basically joining together. England, for example, was joined to France, and you've got Japan joined to Korea, and you got very easy island hops to get from the Asian mainland to Australia. But with the rising of the sea level, that wasn't possible. And incidentally, there's actually an historical record for this dramatic rise of the sea level. It's present in the totem poles that are on the Queen Charlotte Islands off of the mainland from British Columbia. Those totem poles have been dated, thanks to carbon-14, to be about 10,500 to 11,000 years ago. And the totem pole carving basically documents that there was an extremely rapid rise of sea level between 10,500 years ago and 11,000 years ago. So rapid that the Queen Charlotte Islands, which were attached to the British Columbia mainland, became separated, and the people living on the Queen Charlottes were actually contemplating, according to the totem pole record, migrating back to the mainland. But the sea level rose so fast that that wasn't possible. So those people on the Queen Charlottes literally were cut off from the rest of humanity until modern boats made it possible for people in the mainland and people in the Queen Charlottes to go across the Hecate Strait. And that actually ranks today as the oldest written record amongst humanity, the earliest known written record. So yeah, we're often taught in school that the earliest written record dates back about 5,500 to 6,000 years ago. And the Queen Charlotte's, it actually goes back 11,000 years ago, thanks to those well-preserved totem poles. But the larger question that Doug is asking is, what about this Pangea? Almost every younger creationist that I've engaged actually believes that there was a Pangea. They date it much later than what geophysicists date it. I mean, if you look at the geophysical date you see in the textbooks, Pangea existed 250 million years ago, and then the supercontinent split apart. And yes, we do have Africa joined together with South America, and South America splits off from Africa. And what you notice is that part of the eastern coastline of South America, if you actually take it out to the point of the where the continental shelf drops off into the deep ocean, if you match that point, not the land, not the present shoreline, but the place where the continental shelf drops off into the deep ocean, if you match eastern South America with Western Africa as continental shelf, you get a perfect match. And so that's why geophysicists are convinced that South America broke off. The dates are all accurate in terms of the African dates and the South American dates. you can actually see animals and plants on both continents that can be traced back to that time, and geological features that you see on the mainland of South America and Africa. If you put the continental shelves together as two continents, those features actually seamlessly match up, again providing evidence that we're part of the same continental mass structure. Incidentally, we got similar evidence for Antarctica being joined to Australia, and Australia and Antarctica actually being joined to South America. And I've documented all of this in my book, Improbable Planet. So you can go there and see that there is this history there. In fact, what you'll see in Improbable Planet is we now have the geophysical evidence that we can trace back 6 different supercontinent cycles. The supercontinent cycle lasts about a 500 million years. And so we got Pangaea intact 250 million years ago. And the supercontinent cycle is one where you got this huge supercontinent that, thanks to tectonic plate movement, splits apart into multiple continents. They spread out from one another, and they come back together and form a supercontinent. So you got this continent that splits apart and then comes back, splits apart and comes back, and we can literally trace 6 such supercontinent cycles in the past history of the Earth. And Doug is correct that the continents started off as just a few small island continents, and 3 of them exist to this day. Greenland, we have a craton in Western Australia, and there's another craton in South Africa. These were small islands about the size of New Guinea today, that exist today, that date back more than 3 billion years. But beginning about 2.45 billion years ago, we see dramatic growth in the continental landmass. You go from less than 2% of Earth's surface covered with continents to, in a very short period of time, more than 27% of Earth's surface being covered with continents. And we now understand that the first great oxygenation event played a significant role in all these continents appearing at that time. But once you got that 27% continental mass coverage, this is when we can see this supercontinent cycle in operation. As I mentioned, almost all young Earth creationist leaders do believe in this supercontinent cycle, but they disagree with the scientific community and with those of us with reasons to believe in the dates they assign for it. So for example, in the young Earth model, you got Pangaea in place before Noah's flood, and during the 5 months of Noah's flood, this supercontinent splits apart into the 7 continents we see in the face of the Earth today. And I've critiqued this in my book, A Matter of Days, and in Navigating Genesis, basically making the point, Navigating Genesis is where I've done it most thoroughly, making the point that for that model to work, you need thousands of miles of lateral plate tectonic activity being squished into a 5-month window, and tens of thousands of feet of a continental uplift, again being pushed into a 5-month window. And a young Earth creation has argued that can happen if we were to speed up the isotope decay of potassium-40, uranium-238, and thorium-232 by a factor of 1 billion times. If we speed that up, that'll generate the rapid plate tectonic activity. The problem is, if you speed up those radiometric decay rates by that much, you'd basically vaporize all animals on the face of the Earth. You'd actually vaporize all the liquid water on the face of the Earth. Young Earth creationists who've actually studied this recognize that this is a significant problem in their global flood model, particularly the radiometric decay of potassium-40, because all life is loaded with potassium-40. It's radioactive, but it has a very long half-life, more than 10 billion years. You just speed that up by a factor of 1 billion times, you've got enough heat release that's literally going to vaporize your body instantly. And according to Genesis, that did not happen to the people on board the flood. on board the ark or the animals on board the ark. And moreover, it's in direct contradiction to several biblical statements that tell us that the laws of physics do not change. As God is immutable and doesn't change, likewise the laws that God set up to govern the heavens and the earth, Jeremiah 33, do not change. And young earth creationists in their rate study, their published rate study, acknowledge if the radiometric decay rates of these long-lived radioisotopes don't dramatically change, then both the earth and the universe must be billions of years old. But I would argue, based on the Bible alone, we could rule out that possibility. But if you want more details, check out my books, Navigating Genesis, and the second edition of A Matter of Days. In the second edition, I updated the arguments based on our latest measurements. And again, you can get free chapters at reasons.org/Ross.
Hugh, Doug had a follow-up question, which was, is there any legitimacy to Dr. John Baumgartner's theory or theories of catastrophic plate tectonics?
I'm familiar with John. I've actually met him several times. He's a geophysicist. He's a good geophysicist. But as a young earth creationist, he was trying to build some model of tectonic activity that would speed things up to the degree that they need to defend their young earth model and the global flood model. And initially, he tried to make it work without altering the constants of physics, but discovered that was not possible. So a core feature of his model is that we have these dramatically altered constants of physics, and particularly the radiometric decay rates of the long-lived radioisotopes literally have to be sped up by a factor of 1 billion times to make his model work. Number one, the Bible rules that out when it says that the laws that govern the heavens and the earth are fixed, they don't change. Number two, astronomical measurements rule it out, because in astronomy, we can look at distant stars, and because it took light time to travel from the stars to our telescope, we can measure the radiometric decay rates of potassium, uranium, thorium, and other radioisotopes, and just see what the decay rates were in the past. And they measure identical to what we measure in the lab today. Likewise, we can see the daughter products of radioisotopes on the Earth, particularly the daughter products of thorium decay, uranium decay, and plutonium decay. There was plutonium on the face of the Earth when the Earth was very young, and that plutonium decay did leave isotopes, stable isotopes, that allow us to determine what the past radiometric decay rates were. And those stable daughter products tell us there's been zero change in the radiometric decay rates over the entire history of the Earth. And so if something dramatic happened at the time of the flood, there'd be no way that we wouldn't be able to verify that with measurements of these daughter products on the face of the Earth and the measurements of the radiometric decay rates in distant stars.
Thank you. We have a question from Tim Hogel. A question not answered last week. Tim Hogel from the LA area asks, last week you defined the different exoplanet types based on the sizes and distances of solar system bodies and sizes as the defining units. What didn't come across, but seems important, is the relative sizes and temperature categories of these exobodies in the context of the host star itself. It seems to me that the host star's size and temperature should influence the defined distances of warm versus cool and cold versus cold versions, as well as their orbital dynamics.
Yes, good point. And people do take that into account. There you're dealing with measurements that are a little more difficult to make up bigger error bars. And, but yeah, it's true. I mean, what you discover is that a planet wouldn't be warm if indeed, and close if indeed the star were a lot cooler. I mean, the vast majority of stars are a lot less massive than the Earth, therefore they're cooler than the Earth. And so when people talk about liquid water zone planets, most of these liquid water zone planets that have been discovered are planets that are orbiting very cool stars. in which case you got the planet orbiting more closely to the star. And I didn't really get into this last week, but there's one reason why I'm really focusing on the orbital distance from the star, because the orbital distance from the star is crucial for the liquid water habitable zone to overlap the ultraviolet habitable zone. That's just 2 of the 13 known habitable zones. And so just simply recognizing that we not only have a liquid water problem for light to be possible on the planet, we've got an ultraviolet problem. And for the ultraviolet habitable zone to overlap the liquid water habitable zone, you need an orbit that's virtually identical to the orbit of the Earth about the sun. So the real question now is, in all these exoplanetary systems, what's the possibility of having a rocky planet orbiting a host star that's virtually identical to our star, the sun, where that planet orbits the same distance from the star as the sun or Earth does the Earth. And so once you get beyond just looking at the liquid water habitable zone, then suddenly the orbital distance of the star becomes a very important feature. And this is now beginning to be recognized in the scientific literature on exoplanetary systems. But I do agree, if you were to go back even a year ago, this was not well recognized in the scientific literature. But one reason why you see this classification system, by the way, it's not my classification system. I've borrowed that from the scientific literature and exoplanetary systems. And one reason why they've chosen to classify that way is how easy it is to measure the orbital distance of a planet from a star, and how easy it is to measure the diameter of the planet. And so that's where we got our best measurements, and is where we got the most extensive measurements. If you actually just Google exoplanet catalog, 2 catalogs will pop up, one managed by NASA, the other managed by the astronomers at the Paris Observatory in France. And actually, they're now a much bigger team. It's called the Exoplanet Team, but it's that European catalog that gives you the most details. But a quick look at that catalog shows you where we got a wealth of measurements and where we got a great void. And so where you got the good measurements is on the mass of the planet, on the orbital distance, how many days it takes to orbit about the star, and the eccentricity. Other features, it's fairly sparse.
Thank you. Chris Thompson from Anchorage, Alaska asks, Antarctica seems to be radically warming. Could you please comment on the reasons for this and possible short-term results?
Well, there's some debate about whether Antarctica really is warming. There's no doubt that the Arctic is warming. And given that he's in Alaska, the Canadian North and significant parts of Alaska are where we're seeing the greatest warming effect on planet Earth. In fact, parts of northern Canada are warming at a rate that's 5 times greater than the global average. Antarctica, it's much more challenging to determine what's happening. What we do see, however, is evidence of a warm Antarctic ocean water coming into contact with the ice sheets of Antarctica that make contact with the seawater. This is where we're seeing significant melting, and it's basically this ocean water flowing underneath this ice that's being pushed off the continental landmass of Antarctica. And so it's being warmed from underneath, where this ocean water comes underneath, it's been heated up, and it's actually melting the ice and causing significant melting. But it's still an open question whether or not the tonnage of ice in Antarctica is shrinking, growing, or stable. And so that's now a major effort, is to get sufficient research going in that area to determine what's happening. But there's no doubt that there is melting of Antarctic ice as a result of warmer ocean water in the South Ocean coming in contact with those ice sheets that are spilling off into the ocean.
Thank you. Craig McMahon asks, how do you look at the pattern of human migration over Earth, given that there appear to be human remains in Africa at least as old as many in the Middle East.
Yes. This past Monday, I released a fairly long blog, basically dealing with the subject of the dates we have for early human origins. I was basically making the point that carbon-14 dating ceases to be reliable once you get older than 40,000 years ago, and certainly when you get older than 45,000 years ago. And you really don't pick up any good radiometric dating tools until 250,000 years ago. And so we got this gap between about 40,000 years ago and 250,000 years ago, where we don't have really good dating methods. We do have methods. There's about 4 that are very commonly used, but they all have significant systematic effects. They're basically indirect methods. And when you're using indirect methods, you can have significant systematic effects. And what I mean by systematic error is where, because of some unknown feature you don't understand about the environment or about the instruments you're using to make the measurement, or assumptions you're making about the physical processes, the measurements that you're making will have statistical errors where you got plus or minuses, but because of the systematic effects, those measurements could be shifted upwards or downwards in value. It basically shifts all the statistical measurements in one direction or the other. And what you'll see in that article, it's available under my Today's New Reason to Believe on the reasons.org website. And I got a long list of citations there you can check out, is that these methods can be up to having systematic errors as large as 2,000%. And a classic case of that is where the Jimnian cave in Australia was cited as having the oldest dated evidence for human remains and human artifacts. And for 40 years, the textbooks were telling us, based on this Jimnian cave, that Aborigines have been in Australia continuously for the past 60,000 years. And what happened a few years ago is they went back and took those same artifacts and found a way that they could find carbon. And so they're able to do carbon-14 dating. And what they thought was a 60,000-year-old sample turned out to be a 3,000-year-old sample. So basically, it was off by a factor of 20 times. So that's why I'm hesitant to give a whole lot of credence or accuracy to these dates that they say, hey, we found evidence for human artifacts or human activity in the Levant area of Israel that dates back 80,000 years, or in Southern Africa that dates back 80,000 years. But those dates are all based on these indirect methods where we've got huge unknown systematic effects that could throw the dates off. It does help if you've got multiple independent indirect methods, but it's also possible that those methods are all subject to similar systematics. And what I do show in that article is that when you actually look seriously at the systematics, what's interesting is that these systematics all tend to shift the dates to older dates. And so we might be best to look at those dates, 80, 90,000 years ago, 60,000 years ago, as upper limits. It could be that old, but it also could be younger. And basically, I'm making the point that we need to understand not just the statistical errors. And that's the problem when these scientists publish their dates in the scientific literature. Typically, all they give you are the statistical errors. They might mention briefly what they think some systematics are, but they won't give you a number. The reason they don't give you a number, they don't know what the number is. I think it's important for lay readers to realize there's a huge difference between the statistical errors and the systematic effects. And if the paper doesn't state the systematic effects or give an analysis of the systematic effects, you need to be aware they're there and they could be huge. And just to give you an analogy, when you read the physics literature or the astronomical literature, when they publish a measured result, they will give you the result along with the statistical error and the systematic error where they actually put numbers, because physics and astronomy being orders of magnitude simpler than the life sciences, we can actually identify the systematics and determine how big or small those systematics are. But that's missing in the life science literature. That's why I wrote the article, because a lot of people don't understand this difference between publications in the physical sciences and publications in the life sciences. Anyway, it got posted this past Monday. Urge you to check it out. I also point out that even with carbon-14 dating, there are systematics, but the systematics are nowhere near 100% or 1,000% or 2,000%. Typically, the biggest systematics you get with carbon-14 dating are at 15% and typically at 10% or less. So yeah, even with the carbon-14 dates, we need to be careful not to assign as much accuracy as what you often see when only the statistical errors are listed.
Thank you, Hugh. Stephen Posta has a question. Some astronomers are putting forth the theory that Planet 9 may not indeed be a planet at all. They propose the idea that it instead might be caused by a primordial black hole. Primordial black holes are believed to have popped into existence within the first few fractions of a second after the cosmic creation event. Their existence is yet to be confirmed. If indeed the solar system has picked up one of these rare occurrences, does that add on to the uniqueness of our system?
Interesting question. Yes, there's a lot of speculation that there might be a ninth planet in our solar system. And that's because we see kind of a congruence of orbital overlaps of bodies in the Kuiper belt of comets and asteroids and in the scattered belt. And that overlap, people have been speculating, might be due to the gravitational influence of a very distant Neptune-like planet in our solar system. This recent paper is speculating maybe it's an encounter of one of these primordial black holes. Other papers have been published where saying a close encounter with a star to our solar system also could explain that knot. But there's a search going on to see if they can find that planet. It's not going to be easy because of that overlap of orbits of these distant comets and asteroids indeed is indicative of, is indeed caused by a planet. That planet would only be 10 times the mass of planet Earth, and it'd be 50 times as distant in its orbit as Neptune is in the orbit about the sun. So it's very distant and not that big of a planet, and it's going to be extraordinarily difficult to detect. But a search is underway. But yeah, there are papers on both sides making the point that it could be caused by a ninth planet, could be caused by some kind of stellar encounter. I'd be very skeptical about these primordial black holes. Again, you can search. A little tip here, you can go to ADS, www.adsww.harvard.edu. Actually, typically just put in the ADS. That's enough to pop up for you a website maintained by NASA where they basically archive all the research papers published in the physical sciences, not all, but virtually all. And you can go there and search and quickly dredge up all the papers that have been published on speculations and measurements about these tiny primordial black holes that are hypothesized to be produced in the very early history of the universe. I can share with you that there is not a scrap of observational evidence yet to support this. The speculations are still going on, but there is no observational support for that. Most of my peers would argue that those black holes don't exist, just like a number of speculative particles that we thought might be produced, faster than velocity of light particles, tachyons, etc. We're not finding those either. So, but yeah, I would simply go to that website. You can get a quick search of those papers. Usually the abstracts are easy to read and they're always freely available to the public.
You would say that URL one more time very slowly so I can type it up.
adswww.harvard.edu. I mean, you got PubMed for the life science papers, and then you got this harvard.edu with the ADS in front for the physical science papers. So that's the remarkable thing about living the 21st century, how easy it is to access science research papers thanks to these two different organizations archiving all the papers that are published. And what's also wonderful too, they not only archive the published science papers, they alert you to the preprints that are just coming on board. So they'll give you the preprints as well.
Hugh, thank you very much. We're out of our recording time, so we're going to have to let you close it up. We have one question pending, but we can answer that one at the start of the next one, if that would be okay.
That'd be great. I've stopped the recording, and yes, come with your questions next week. And next week, I'm going to try to finish this session on these gas giant planets and why they're so important for existence. That'll be next week, so tune in. And with that, let me close our time out in prayer. Father in heaven, we want to thank you for the privilege of being alive at a time when you're revealing so much through your book of nature, and how we can use this being revealed in the book of nature to verify that what you've recorded in the book of scripture indeed is inspired, it is inerrant, it is authoritative. It's a book that we know can come from you because of the evidence we have from nature that what's revealed there indeed is the error-free word from you. And Father, I pray that you would give all of us opportunities to share with others just how indeed you've given us two books, how they corroborate one another, and actually they give us a pathway to eternal life with you. In Jesus' name, amen.